Okay, so for AP Chemistry, we left off on practice problem 6.1.3, acidic salts, part 2. And we're looking at page 353, practice problem number 1. It says that iron 3 nitrate solution are used by jewelers to etch silver and silver alloys. Calculate the pH of this concentration of an iron 3 nitrate solution. So what we should do is we should write out the dissociation equation for this iron 3 nitrate, which is going to be an iron 3 ion and 3 nitrate ions. The concentration of the solution is 6 molar, which means the concentration of the Fe plus 3 and the NO3 minus 1 are both, 6 molar. This is 18, my bad, because there's a 3 in front of it. So you want to multiply the 3 times 6 to give you 18 molar. Now, this right here hydrolyzes. So what that means is we're going to take the Fe with water, and this is one of the hydrated cations on the previous page. And what this is going to do is it's going to form an acidic solution when it hydrolyzes, and you're going to be left with 1 less water. We add a hydroxide to the formula and we change this charge from a +3 to a +2, okay? And then you're going to have a hydronium ion coming out on the product side. If you do your ice table, this concentration is 6 molar. We don't write anything for the water. You have 0 molar for each one of these products. This is minus X, plus X, plus X. This is 6 minus X, X, and X. We assume that this is just 6 molar for the equilibrium concentration. We can ignore the minus X. Your Ka is going to end up being X squared over 6. If we look at the Ka value in the table, it's 6 times 10 to the negative third. If you solve for X, you're going to get 0.1897 molarity. This is the hydronium ion concentration in your ice table right here. So what you can do is to get the pH, take the negative log of that value, which is going to be 0.72. Okay. Now, as we move on, we're going to be looking at salts containing weakly acidic cations and weakly basic anions. So if you go to the next page here, a salt containing a weakly acidic cation and weakly basic anion will produce a solution that is acidic if the Ka for the cation is greater than Kb for the anion, basic if the Ka for the cation is less than the Kb for the anion, or neutral if the Ka for the cation equals the Kb for the anion.
Pardon this interruption. Founders Hall main floor will be closed today for event setup. The outside walk-up windows.
Let's look at the quick check. Which of the following salts will dissociate into ions that will both react with water?
Use the outside stairwells to access your second floor Founders Hall classroom. Once again, Founders Hall main floor is now closed for event setup. Thank you.
In each of these compounds, I'm showing you what the ions are individually. This is actually C2H3O2, which you're a little more familiar with. This is NH4 plus 1, NO2 minus 1. And for instance, here, the Ka of NH4 is 5.6 times 10 to the negative 10th. The Kb is 2.2 times 10 to the negative 11th. And so if you look at the relationships here, you can see that based upon the substances that I had written on a previous page, these contain ions that will allow them to both react with water. And number two, they want us to write out two hydrolysis reactions that occur when a sample of NH4F dissolves in water. So if you've got your NH4 plus 1 in water, what's going to happen is a hydrogen will join the water. You'll get NH3, NH3O plus 1. For the F negative one, you're going to have a hydrogen given to it, and you're going to form HF and OH minus 1. The Ka for this is 5.6 times 10 to the negative 10. That's for the NH4 plus 1. And then this Kb is 2.9 times 10 to the negative 11th for F negative 1, okay? So which of these two hydrolysis reactions will happen to a greater extent? Well, you compare the Ka and the Kb. The Ka for NH4 plus 1 is greater than, because it's 10 to the negative 10th, and the 10 to the negative 11th is for the Kb. So the hydrolysis of NH4 plus 1 will occur to a greater extent for the NH4 plus 1 because of its Ka value, okay? Now, if you take a look at page 355, let's look at the practice problems here. This says, arrange the following 0.1 molar salt solutions in order of decreasing pH. Okay, so this FeCl3, this is the conjugate base of a strong acid, HCl, okay? And then this NH4 is the conjugate base of a very weak acid. Therefore, it's a strong, weak base that accepts a lot of hydrogen ions, okay? Then this substance here is the conjugate base of a weak acid, acetic acid, okay? And then this substance here is the conjugate base of HNO3, which is a really strong acid. So when we order these, I would put the NH4 2CO3 here, followed by the NaNO3, and then the AlC2H3O2 here. And then lastly, I would do the FeCl3, because when you've got these 3 chloride ions, they won't accept, absolutely would not accept any hydrogens, because that comes from the strong acid HCl, which completely dissociates, and it will never accept hydrogens, okay? Now, down here, when they talk about salts containing the cation of a strong base and an amphiprotic anion, these are the rules governing the solutions. They're acidic if the Ka for the anion is greater than Kb for the anion, and they're basic if the Ka for the anion is less than the Kb for the anion. They've given a summary of everything discussed here in this table. If you turn to the next page, let's take a look at some practice problems here. Determine if a 0.1 molar solution of K2H3PO4 will be acidic or basic, and include the hydrolysis reactions that will occur. So if we've got HPO4 negative 2 in water, what's going to happen is this is going to give a hydrogen to water, and you're going to get PO4 negative 3 with H3O plus 1. This Ka is 2.2 times 10 to the negative 13. Okay, then we've also got HPO4 negative 2 plus water and you could have hydrogen being given to it, which means this would end up being H2PO4 -1 plus a hydroxide. Okay, so this Kb will be 1.6 times 10 to the -7th. Okay, so really, if we look at these relationships, the Kb is greater than the Ka. So this would be basic. Okay. Okay, then let's do number 2. Arrange the following 0.1 molar aqueous solutions in order of increasing pH. So I'm going to go ahead and highlight these anions here. And for our K+1 and HSO4 -1, this is the conjugate base of a strong acid. So that means that it cannot accept a hydrogen from water, okay? And then if I'm looking at Na+1 and HSO3 -1, this is the conjugate base of a stronger weak acid. So therefore, it has a weaker conjugate base, and it doesn't accept hydrogens often. Okay, then if I look at Li+1 and HCO3 -1, this is the conjugate base of the weakest weak acid. Okay, so what that means is that this is a stronger conjugate base and it accepts hydrogens from water. Okay, so when we go to order this, you would want to order it as KHSO4, NaHSO3, and LiHCO3.